So, as I talked about last time, calcium is the dominant cation in extracellular fluid, and potassium is the dominant cation in intracellular fluid. So, if we start looking at the rules of electrolyte balance, so usually the most common problems with electrolyte balance are the imbalances between gains and losses of sodium ions, and so sodium is a culprit in a lot of things that go wrong within our system. So problems with your potassium balance are a lot less common, but they are actually more dangerous than sodium imbalances, and we'll talk about some of the things that can actually cause potassium imbalances to take place. So potassium balance, basically you want your potassium gains to equal your potassium loss. So most of your potassium gains are through your digestive tract. We get about 100 milliequivalents per day, and your major loss is basically through your kidneys, and your extracellular potassium regulation is done by the kidneys. Since your intake is usually about 100 milliequivalents a day, so the kidney gets rid of 100. It is controlled by aldosterone, regulating sodium-potassium exchange pumps in that distal convoluted tubule and the collecting duct of those nephrons. So if we have low extracellular fluid pH, it can cause the hydrogen ions to be substituted for potassium, and this can actually lead to increased amounts of potassium in your circulation. So potassium is highest in the intracellular fluid. And due to that sodium-potassium pump, we're looking at about 135 milliequivalents per liter in the intracellular fluid compared to about 5 milliequivalent per liter in the extracellular fluid. So it's definitely higher levels in the intracellular fluid. So let's look at some factors that play a role in tubular secretion of potassium. So obviously the potassium concentration in your extracellular fluid will determine how much your kidneys are going to excrete. Changes in pH, as I just talked about. A low pH is going to cause the body to get rid of the hydrogen ions in exchange, and get rid of the hydrogen ions in exchange for sodium instead of getting rid of the potassium ions. And then aldosterone levels will also factor into the secretion of potassium. So changes in your concentration of potassium ions in your extracellular fluid, you're going to have higher extracellular fluid concentration. Increases your rate of secretion, obviously. When we talked about the low pH, a low pH lowers your peritubular fluid pH, so the hydrogen rather than the potassium is exchanged for the sodium in your tubular fluid, and the rates of potassium secretion declines. And then aldosterone kind of affects the potassium loss in the urine, so those ion pumps reabsorb the sodium from the filtrate in exchange for the potassium from the peritubular fluid. So, and when you have high potassium plasma concentrations, it's going to stimulate that aldosterone, which will then reabsorb the sodium, and you will lose the potassium. So, things controlling the potassium, we just talked about that. So we take in about 100 milliequivalents liter per day from the intestinal tract. So we have higher levels of potassium inside the cell than outside, controlled by that sodium-potassium pump, 3 sodium out, 2 potassium in. And then we know that we can lose potassium through the kidneys, but most of the time it's equal to our intake. So 100 milliequivalents per day of loss, 100 milliequivalents a day of intake. This chart is wrong. It says factors promoting hypokalemia. Over here, factors promoting hypokalemia, so we can't have it go in both directions. So this is hypokalemia, this is hyperkalemia. So hypokalemia, we're looking at the diuretics, and if you have someone that's taking diuretics, you need to be very, very careful because they can go into a hypokalemia state very, very easily. Hyperaldosteronism, and then over here we're looking at low pH kidney failure, and a lot of drugs can cause you to go into hyperkalemia. So we know that when you have mineral balance, we're looking at a balance between your ion absorption and your ion secretion or excretion. We know that most of our intake we take in through our mouth, intestines and colons, and then we lose a lot of it through our kidneys. We lose some of it through our sweat glands also. And then we know that most of our minerals are reserved, our reserves are in our skeleton. So if we look at this image, you can see absorption, intestinal system going into our intracellular fluid and extracellular fluid. It's going to go back and forth between our ion reserves. We do have some loss through our sweat glands, and then we have most of the loss that takes place in the kidneys. So these next few charts, I don't expect you to know all this information, but it might be just a nice refresher on what some of the electrolytes are and the mechanisms that transport them along the digestive tract, where the absorption along the digestive tract. These are some of the key minerals and their routes of excretion. So urine and feces, basically, we do know that sodium comes out in the sweat, but most of the other ones are urine and feces. And then these are some of the minerals, and again, urine, we lose some zinc through our hair, but urine and feces are the routes of excretion for those also. You might want to take a look at some of the functions, just to refresh again what some of the functions are of these minerals. So we talked about the natriuretic peptide in the last discussion, but if we look at homeostasis here, so we have a rise in our blood pressure and blood volume that takes place either by gaining fluid or by sodium gains. So you're going to have pressure in the arterial, you're going to have some arterial distension. Those natriuretic peptides are going to be released, so increased sodium loss, increased water loss, decreasing your thirst, and then inhibiting everything that would increase fluid within your body. So you're going to decrease your blood volume, you're going to have reduced blood pressure, leading to homeostasis being restored. So if you have a fall in your blood pressure or falling blood pressure and volume, so you're going to have your endocrine responses kick in. So increased renin secretion from the juxtamedullary complex, right there by the renal corpuscle. So the renin secretion, so you're going to have angiotensin II activation, where you're going to have increased aldosterone being released from the adrenal gland. It's also going to stimulate that ADH release, so increased urinary sodium retention, decreased water loss, increased thirst, increased water intake, returning your blood volume back to normal, hopefully. And then this is the role of the aldosterone-sensitive exchange pumps. So this is your aldosterone-sensitive exchange pump. So your tubular fluid is going to bring, aldosterone wants to hold on to sodium, so it's going to bring the sodium back into the cell in exchange for the potassium. So the potassium is going to go into your tubular fluid. But first it's going to pull the sodium or the potassium out of the extracellular fluid. That's going to be exchanged for the sodium in the intracellular fluid, which will then deliver it to your extracellular fluid. So this is your sodium potassium pump, 2 sodium out, 3 sodium out, 2 potassium in, and this is the sodium potassium pump that is aldosterone sensitive. And then again, this is normal. Normally you have the sodium potassium pump that's exchanging the sodium and the potassium. When you have increased hydrogen ions, it's going to be exchanged, the hydrogen ions are going to be exchanged for the sodium instead of the potassium. So you're going to have to, you're going to end up with rising potassium levels in the extracellular fluid because of that, because it is not released like it normally is. So hypokalemia, we're looking at below 2 milliequivalents in the plasma. So this can be caused by diuretics, and so like I said, if someone is taking diuretics, you need to watch them very closely for hypokalemia. If somebody may have abnormal secretion of aldosterone or aldosteronism, they're going to have muscular weakness, they're going to have paralysis, and it can be potentially lethal, affecting their heart if it is not increased. And then hyperkalemia above 8 milliequivalents per liter in the plasma. So really chronically low pH, you would have you'd be holding on to all that potassium because it would not be exchanged for the sodium. Kidney failure can cause this, and there are some drugs that promote diuresis, and they would, by blocking the sodium-potassium pumps. Muscle spasms, including heart arrhythmias, can be the symptom of hyperkalemia. So acid-base balance is next.